Reaction rates are dictated in part by the energetics of the individual bonds that break and form during a reaction. Let's use this reaction as our prototype. CH3I, which is called methyl iodide, reacts with hydroxide ion to form iodide ion and CH3OH, which is methanol. This is the forward process indicated by the letter F. This is a reversible process, so reading the reaction backwards gives the reverse process, indicated by the letter R. What I have here is a model of CH3I and a hydroxide ion. In hydroxide, the oxygen is black and the hydrogen is red. In CH3I, the silver sphere in the middle represents carbon, with the 3 hydrogens on the right and iodine in purple on the left. Now, don't worry about the sizes. Iodine really should be the biggest one of these. But that's not the point. What we're trying to do is see how this reaction proceeds. So we start with our reactants, CH3I and hydroxide. And the way this reaction is believed to occur is that hydroxide comes in from the opposite side of the iodine, a new CO bond forms, the hydrogens push over, and the old Ci bond breaks. Now this is a reversible process. We can reform the Ci bond, push the hydrogens back over to the right, and break the old CO bond. And it can go back and forth in a reversible process, forming products or going back and reforming the reactants. Now, what you'll notice about this is regardless of which end we start with, when we partially form the new CO bond, the hydrogens go halfway over. We've partially formed the new CO bond, partially broken the old Ci bond, and still have 3 hydrogens in the middle. Now, this is actually going to be a higher energy configuration. Carbon has 5 bonds around it. It really only wants 4. Carbon really wants 109-degree bond angles, but there are 90-degree bond angles in the molecule. This state is called the transition state, partway between reactants and products. If we continue the reaction, we end up with the products, with the Ci bond broken. But what you'll notice is, regardless of whether we did the forward process or the reverse process where we're reforming the Ci bond and re-breaking the CO bond, we go through the exact same transition state. Again, in the same transition state, whether we do the forward process or whether we do the reverse process. So here are our 3 situations. The reactants on the left have the Ci bond intact. In the middle is the transition state, where the Ci bond is partially broken and the CO bond is partially formed. These partial bonds are indicated by dashed lines. On the right are the products, with the new CO bond intact. What we want to do here is to plot energy, in this case potential energy, on the y-axis versus what is sometimes called the reaction coordinate. This rather generic term simply follows this one set of molecules shown at the bottom as the Ci bond breaks and the CO bond forms. And that is a point to make. This plot is for a single pair of molecules. Looking at bond energies, we know that the CO bond has a greater bond energy than the Ci bond. It is a stronger bond. If you recall our discussions of bond strength and bond energies, stronger bonds with greater bond energies are at lower energy. The CH bonds and the OH bonds all stay intact. So for this system, the reactants are at higher potential energy and the products are at lower potential energy. The transition state, with 5 bonds around carbon and 90-degree bond angles, is at higher energy still. As bonds are breaking and forming, the energy is constantly changing along the reaction coordinate, so we usually see a curve like this. There are 3 energy changes of note in this diagram. First, The difference between the energy of the reactants and the products is delta E, the potential energy change for this set of molecules and ions. In this example, with these reactants, delta E is negative. But notice there's also an amount of energy that needs to be added to the reactants in order to start breaking the Ci bond and start forming the CO bond. In other words, there is an amount of energy that needs to be added to the reactants to get to the transition state. We call this the activation energy for the forward process. It is given the symbol E sub A, F. For the reverse reaction, there is also an activation energy, the energy required to go from the products to the transition state. This is given the symbol E sub A, R. Notice that the two activation energies are different. It takes less energy to get to the transition state from the reactants than it does from the products. This will have an effect on the reaction rates, as we will see in an upcoming page. One final point to make. Although this is technically a plot of potential energy, we know that potential energy changes are part of enthalpy changes. So we will use the potential energy as a proxy for enthalpy. In this example, since delta E is negative, we will also assume that delta H is negative. So this is the picture for an exothermic reaction.